let me welcome everyone to this platform. We have another astute personality to present to us a research, and it's in the name of Dr. Anna Thompson, who is a senior lecturer at KNUST, and also the head of department of meteorology and then climate science. He is a climate scientist with the expertise in climate modeling and then evaluation. And also he has the vast knowledge in environmental data analysis with the application of several Earth data analysis tools. I mean, he has that experience in that. Today he's here to present to us on a topic titled the West African heat slope, heat band, and then the rain band. The three signatures of African monsoon system for process-based climate and then model evaluation. So without much ado, I introduce to you Dr. Anno. So Doctor, I'm going to stop sharing so that you take over.
Thank you very much.
Welcome.
So can I share my screen?
Yes, please, you can share.
Thank you very much. And thank everybody for making time for this presentation. As Samuel said, the topic for today's presentation is the West African heat low, heat band, rain band, three signatures of the West African monsoon system for process-based climate model evaluation. Actually, this work was funded by the Future Climate for Africa project called the Launchpad. So the Launchpad was a project that was structured for model evaluation hub for the West African region. So this project was actually instituted to for connecting UK modeling and then African expertise among these institutions. Oxford, University of Oxford, the Met Office from the UK, and then other institutions, including KNUST on the African continent. So the program is through fellowships. Among these are the members, and then what the program seeks to do is to actually have a development of tools that can be used for evaluating climate models. So in the CMIP 6, we have what we call the F system model evaluation to the ESM VAT SAT2. So this project was instituted to bring the African contribution to that tool. So the whole structure of the project was that we'll develop automated evaluation tools for climate models where researchers analyze key processes in models, and then researchers work with software engineers to develop tools, and specifically these tools will be added to the Met Office Auto Assess Evaluation System, and then on the broader scale, these two will be included in the F system model evaluation tool, and that is embedded in the CMIP 6 infrastructure. So that is this tool, and then that was the main, the structure of the work. So what we did was that we have to bring the contribution of the whole African continent, and therefore we have to divide the groups into various regions over the continent. And then I happen to actually fall in the region of West Africa. So I had to actually look at a key climate system in West Africa or climate process in West Africa that can be used to evaluate these models, and then create a tool which can also be used in the future for model evaluation. So in that regard, in West Africa, we know that one of the key synoptic scale that we have is the monsoon system, that is the West African monsoon system. So I decided that I will look at components of the monsoon system and then use it for the evaluation tool. So that is what I'm coming to present on. And therefore, I decided to use these three processes or features that was mentioned earlier in the topic. So as in a simple term, the West African monsoon system can be seen as a land sea breeze in the simple term. I was told to make the presentation so simple so that people will understand. So the West African monsoon system can be considered as a land sea breeze wind system, whereby in the summer monsoon, that is the wet season, a low pressure system is on the continent, and therefore air will rise from the oceans onto the continent into the low pressure system. And this, when this happens, we see that the ITCZ or the ITD is forced into the northmost position, and below this ITD or ITCZ, we have a lot of moisture-laden air on the continent. And then in the winter or the dry season monsoon system or monsoon season, we have the rivers. So high pressure zone is on the continent, and therefore we know that there will be the divergence, and then air will flow from the continent onto the sea. So here we see that the ITCZ or the ITD is actually forced to the southmost position, and then across the continent or in the region, we have dry and then hazed conditions over the whole region. So we see that this is a seasonal occurrence, and therefore the ITCZ or the ITD actually moves either north or south, depending on where the low pressure or the high pressure is located. So according to Biasitti, the mean position of the ITCZ results in a net energy transfer from the northern hemisphere to the southern hemisphere when we look at this scheme. And this arrangement actually transports heat away from the northern hemisphere, resulting in a transport of moisture into the northern hemisphere, and the ITCZ must shift to the north for this to occur. So the result of this arrangement is that there is a cyclical movement of moisture and then heat bands, and then the heat low over the West Africa on annual basis, forming part of the West African monsoon system that we are all aware of. So in the first time, I tried to develop what we call or define what we call the West African heat band and then the West African rain band, and then added it to the already defined West African heat low to actually assess or evaluate the models, the climate models on these three processes. So the aim of this presentation is to show that indeed the West African heat low, the West African heat band, and then the West African rain band are key components of the West African monsoon system, and therefore they can be used for process-based climate model evaluation. And the specific objectives are to show that and to show the linkages between the three features or the three processes, and then also show some few representations of some few semi-6 GCMs as how they represent these processes or features. So quickly, these are the data set that I use, ranging from ray analysis to observational graded data set. And then here I present only 4 models to you. And the models are named, these are the names of the models, but I have shortened them into model 1, model 2, up to model 4. Okay, so how was the West African heat load determined? Actually, I used the LAVISI 209 approach to determine the West African heat load. And according to LAVISI, I'm not going to delve into much of this. According to the LAVISI, and the West African heat load is just the highest 10% values of what we call the low-level atmospheric thickness. The low-level atmospheric thickness is just a thickness between 2 geopotential heights, and specifically the geopotential height between the 700 hectopascal and then also 925 hectopascal. And then also we did this using the 6 o'clock UTC geopotential. So that is what we use for the heat load. So it is basically an anomaly where we have the highest thickness of low-level atmospheric between the 2 geopotential heights. And then the heat band, which is a new feature or process that I developed, was determined by constructing monthly mean temperature, MMT, and then finding a cumulative probability density function of the MMT on all grades over the region. And then when it is done, then you extract highest 50% values of the MMT. And then those 50% values are determined as the heat band. And similarly, I did the same thing with the rain band by calculating the monthly total precipitation and then finding the cumulative probability distribution function as the MTP on all grades, and then also getting the 50% value of the MTPs. So the rain band and then the heat band is 50% highest value or 50% sort of anomaly of the rainfall or the mean temperature. So after getting all these 3 features, I am going to show the results to you on the results for the annual cycle. We have the heat load from January up to December, and then likewise the rain band and then the heat band. So we see that for the heat load in January, we have a circular heat load with low intensity in the southeastern part of the region. And then moving from January to August, we see that the movement, the heat load migrates from the southeastern part to the northwestern part of the region. And then also the intensity also increases. And then thereafter, it comes back to the original position in the southeastern part in December. So what we can also see is that in the winter season or winter month, that is DJF, we see that the heat band are of circular form or shape. And then also in the summer month, also they are of circular form and then shape. And then the heat load is actually intensified in the summer months, that is June, July, August. And then in the spring or the autumn, we see that the heat low has elongated shape or form. Okay, so we come to the rain band, and then we see that the rain band also follows a similar migration as that of the heat low. It starts in the southern part in January and then moves to the northmost part in August. And then also the intensity increases up to August and then move back to the southern part in December. Likewise, that of the, and then also in the summer months, June, July, August, we see that the rain band is in the northmost position, and then also the intensity is very high. And then the width of the rain band is very, very wide in these summer months. And then we come to the heat band. So we see that the heat band also starts from the southern part of the region and then move to the northmost part in August. So in the winter season, we see that the heat band covers the southern part of the region, and then in the summer time, it covers the northern part of the region. And then also the intensity increases in the summer month, that is June, July, August. So clearly we can see that these three features or processes actually mimics each other, and there is a clear linkages between them in terms of their migration from month to month to the intensity, and then also the intensity, the migration, and then sometimes the fall. So after doing this, I wanted to look at how the models are reproducing or representing these features. So I present to you the first one, that is the West African heat low. So the first two maps are for the first one is for era 5, and then the second one is for era interim, and then the rest are for the models. So you can clearly see that in the array analysis dataset or the two reference datasets, you see that the heat low moves from the southeastern part to the northwestern part in August. And then as it moves north, the intensity increases, and then move back to the southmost position in December, and then the intensity also decreases. So we can clearly see that this in the two analysis data sets. So how are the models representing these structures? So we see that indeed all the models are able to actually represent the migration from the south to the north in August, and then back to the south in December. In all the models, they are able to represent. However, we see a specific misrepresentation of the West African heat low by model 1, that is CNRM CM6-1 model. Especially in the winter time that the West African heat low is very, very intensified. We see that this model is not able to capture that intensity. And then also the form or the shape is not being captured in that model. And another thing is that the model, however, simulates a stronger heat low in the winter months, okay? And then in the case of model 2, we see that although it gets the form or the shape and then the intensity close to that of the reference data sets. But in the core of the simulated heat loads for the model 2, the intensity is quite higher than that of the reanalysis. And in the rest of the models, the intensities are quite weaker, especially in the summer months. And we see that, for instance, in this model 3, we have the winter month is having a stronger intensity than that of the reanalysis. And then this one is also evident in model 4 also. So then I move to that of the heat band. So we also see that for the heat band, in January, the heat band is in the southern half of the region, and then move to the northern half of the region in August with higher intensity, and then back to south in December. So we see that in the two reference data sets. And then again, the models are able to represent the migration of the heat band, but we can clearly see that the model 1 is simulating a weaker heat band for the summer months. Also a bit consistent, but we can see clearly that here there might be certain processes that are contributing to this simulation of stronger heat band on the coast. And this can be attributed to the fact that it has been reported that climate models actually simulated strong biases of sea surface temperature in the Gulf of Guinea. And this may be as a result of that, which could be driven from other processes. So we can clearly see that at least the models, the connection between heat low and then heat band, or the linkage between heat low and then heat band, the model up to this point are simulating that or are representing that fairly satisfactorily. So this is the results for the rain band. So again, the rain band moves from the southmost position to the northmost position in August with broadening of the width and then also the intensity, and back to the south in December. So you see that all the models are capturing the migration. But what we actually see is that, for instance, in model 1, clearly there is a misrepresentation of the rain band in the summer season or the summer months, and which can be attributed to the fact that this particular model couldn't capture the summer month heat low and then the rain band, and therefore it is consistent in the heat low and then the heat band, and therefore it is consistent in also not being able to capture well the rain band, because you see that it is not able to pull the rain band across the continent. It is seen on the ocean. We don't see it across the continent. And then elsewhere, we also see that for model 4, we see that the model is not able to pull the rain band onto the continent. And this could be as a result of the fact that the temperature gradient, which is actually as a result of the heat band constructed, is weaker in the summer months than that of the winter month, and therefore the models are not able to pull the moisture bands onto the onto the continent. So in conclusion, the West African heat low, the West African heat band and the rain band migrate from the south in January to the north in August and back to the south in December for an annual cycle, and with increasing intensity from the south to the north and then vice versa. In general, all the models are able to represent the climatological annual dynamics of all the three processes and the linkages between them, indicating the satisfactory representation of the West African monsoon system in the models. Though we see that differences in the models simulations previous, where also it is also true that where we use more than one reference data set, there are some slight differences in how the reference data represent these features. Okay, so this study presents a crucial pathway for process-based model evaluation for the investigation of what future impact of climate and then climate model development. Because if you want to develop or you want to improve your model, you would like to see how it simulates processes and not just an output, let's say temperature or precipitation. You want to know how the model simulates a process like the West African monsoon or a mechanism, and therefore you target it, and then the results will be better. So this work, as I said, was done as a model evaluation hub for Africa, and then the project was funded by the Foreign Commonwealth and the Development Office. And then when you go to this website, you will find almost all the processes or the features that we actually did the evaluation of the models on, and then the codings on this website. And then you can get more information on the project using this website. So these are the members of the group, and then these are the participated institutions. Thank you very much.
Thank you, Dr. Thompson-Ano, for the great work and then the great presentation. I believe people have really enjoyed it. They surely would have one or two questions to really ask. So for our viewers and then our listeners, and then those who are also joining us for the first time, this particular topic is something very important which would help us understand the dynamics of our meteorological parameters over the entire continent. So without talking much, I think if people have questions, they can type, or either you raise up your hand so that you can be identified to ask your question. So the floor is open. Let me check the message. I think so far, I think there is one person who has, okay, just a comment from Jacob Ajekum, great presentation. Yeah, so the floor is still open. If you have questions, you can ask. I can see Dr. Marian Osei stand up. So Dr. Osei, can you ask a question?
Yes, good morning, and thank you very much, Doc. There are just a couple of questions and clarifications I would like to get. I think I missed what the heat band and then the rain band are supposed to mean, a definition of what exactly these two are. And then you used a threshold of 50% to extract the heat band and then the rain band. So is it possible, or could the models have been improved their simulations of these two variables, they have been improved if the threshold was not 50%, but then it was, let's say, 75%, because we are seeing a very high amount of rainfall over the ocean for, I think, the model 1. Then, even though it extended to the latitudinal extent for the northmost extended to that of the GPCC, but then we are still having so much rains over the ocean. So if there was a kind of very rigid threshold, would it have improved the simulation so that there won't be so much rain over the ocean, or so much representation of the heat band over the ocean, and instead kind of restricted it more to the land to conform with the observations? Yeah.
Okay. Thank you very much. I hope you can hear me, please.
Yes, you can be heard.
Good. Yeah, so in simple terms, the heat band and then the rain band are just areas over the region with 50% higher rainfall when you compare it to the cumulative distribution function. So you actually construct a cumulative distribution function. So you add up all the rainfall on the grids together. And then you say that, oh, the highest the highest rainfall within the region is, let's say, 100 millimeters for a particular month. It's 100 millimeters. Okay, so that is the highest rainfall on, that is the grade with the highest rainfall within that month. When we put all the rainfall, you know, some grade will have, let's say, 1 millimeter, some will have 2 millimeter, until we get the one with the highest rainfall, let's say 100 millimeter. Okay, so that is the highest rainfall in the region on a grade. So then we, out of this 100, we say that all the regions with 50% of this 100 is the, where we say that it is the what? The rain band. So what we do is we subtract 50% of the cumulative distribution function from every grade. And then you see that those that are below will be taken off, and those that are above will be sorted. So all that we are saying is that the rain band is the area with 50% anomaly in rainfall. And then the heat band is also 50% anomaly in the temperature. So it is anomalous heat temperature or anomalous rainfall. And actually the same thing was done for the heat low. The heat low is also anomalous thickness of the geopotential height. Okay, so it's just an area where we see that this particular structure is on the higher side as compared to the average, or compared to what we are supposed to see over there. So in response to whether we increase the threshold or we did, if we increase the threshold, the model are going to do better. They wouldn't do better. They will present the same results because we did the same calculations with the models, and then the observation. So you see here that, for instance, this models, which is having a lot of rain band on the coast, is not bringing the rain band across the continent. There are no rain bands on the continent, especially in the half-eastern part of the southern of West Africa. Okay, so not that we have given it 50%. That is why it is doing that. If should we increase it, it means that it will also not capture that same thing. So should we increase it, what will mean is that we'll see a high resolution of what the overestimation or underestimation, but we wanted to actually look at the process, the whole band. That is why we did that. I hope my question is answered.
Yes, please.
Okay.
All right. Thank you. There is
able to answer all the questions.
Yeah, I think she said it's okay.
Okay. All right.
Said all the questions.
Yeah.
Okay.
Yeah. Now I think there's another comment or question I think raised by Ka. Okay. It says I joined a bit late, but can you explain how the bands stroke low link to the West African monsoon? Yeah, so that is a question that the person is.
Can I explain?
Say, can you explain how the bands or the low link to the WAM?
Oh, okay. All right, of course. Okay, so that when you look at in the case of the rain band, we see that as I explained with the first schematic presentation of the West African Monsoon System. I said that the West African Monsoon System, in simple terms, is a wind, it's a land sea breeze, and then in the winter monsoon, we have the northeast trade wind over the distance. The trade wind is over the whole region, and then we have the high pressure on the continent. So here you can see that on the continent is what has no clouds or no rain bands during the winter period, and then you see that because there is divergence and high pressure on the continent, and then the northeast trade wind prevails, the convergence zone is moved to the southmost position, which can be clearly seen with the rain band. So the rain band is sort of the region of convergence between the two wind systems. So you see that in the winter season, they are forced to the southmost position, okay? And then also in the summer season, they are forced to the northmost position, which is clear evidence of the West African monsoon system, okay? And then when you come to and then when you come to that of the heat band, we also see the same thing, that in the in the winter season, the heat band is forced to the southmost position. And then in the summer, it is forced to the northmost position. And also, the heat low also shows that in the winter, it is forced to the southmost position, and then in the summer month, it is forced upwards to the northmost position. So in a way, a movement of as we can see, the heat low moves to the far north, followed by the heat band, and then followed by the rain band. So as the heat low moves far, it pulls the heat band and then also pulls the rain band, which clearly shows the connection. And then you can see it from, I think this one is clearer. I should have actually put the tray into that long term so that you can see that it is moving from the south to the north in all the three cases, which we know that the summer monsoon brings about a lot of rainfall, and then that is when we have a lot of the heat low actually prevalent. And then this is clearly as a result of the West African monsoon, which is controlled by the kind of the solar revolution of the earth around the sun.
All right, thank you. If I think Prof. Lamte has raised his hand, so I'll give him the chance to. Prof, please, you can unmute yourself to ask your question.
Thompson.
Hello, Prof.
Yeah, congratulations. Good presentation. Can I see the beginning of your slides where you define these indices? Because my question may not be necessary if I can get it from the definition. So the beginning where you define what you mean by heat low, heat band, and the rain band.
The definition. Actually, I haven't given a definition of the. No,
you wrote. Yeah, can I just see the slides? You wrote something there.
This one is this slide.
No. Where you actually indicate. No. I think it's earlier. You have a slide where you show the heat low, the heat band, and the rain band, where you indicate that one of them is the monthly mean temperature, the other one is this.
Okay, this one.
After this, can you go?
Go up or down?
Down. The next slide. Let's check the next slide.
This one.
No. You define, okay. you don't give no, then maybe it's before the objectives. I saw, yeah, this one. I think it's this one. Okay. So in what unit? So your rain band. Right. Yeah, that one. Go back. No. It was correct. Go back. Okay. Yeah, this one is okay.
What I have here is the models. Okay, all right. Okay, so if you
go back. Not this one. The previous one.
This one.
No, the previous one. Before. Yeah. This one is okay. This one.
Okay.
This is what I want.
Okay.
Yeah. Okay. So in what unit is your rain band? Because the legend for your rain band did not have a unit. Is it in millimeters or millimeters per day?
Oh yes. Yeah, it's actually millimeters. Yeah, so it's I show. Let me see. Okay. Oh, okay. The unit. Let me see here. The unit couldn't come. Actually, the units are millimeter.
Okay, but you can tell us. Yeah, is it millimeters or millimeters per day?
Yeah, it's millimeter per day. So
millimeter. Okay.
For instance, you find the total monthly precipitation for, let's say, December, January. For I took for the total precipitation for monthly total.
Okay, monthly total. Okay.
Monthly total precipitation. Okay. Of course, this is climatological presentation. So we did
that's fine. So it's just climatology.
Yes,
now, do you have plans? Now my question comes: do you have plans to go beyond the climatology and see how these systems behave in future climates?
Yes, of course. Actually, this part of work, we have submitted it for publication, and then and the next part is to also look at how the models will do the simulate the future, simulate the process in the future, and then see how the future state of these processes are going to actually, is going to be like with the models, and then also try to see how the West African monsoon in these three components are going to look like in the future. Of course, another important thing is that this project actually was a follow-up to that of the Impala project, which you actually connected.
I can see that. Yeah.
So we needed the model community needed a feedback as to what is going on wrong, so that they can actually work on it in their models. So, and that is why we targeted process and not outputs. So, so that you look at how the process are also being represented by the model. So, indeed, we are going to do another work whereby we'll look at the future and then see how these features and then processes will look like. And of course, we can also, there is a plan with my student that I want him to also look at how these processes or features are simulated with different schemes of the WAHB model, so that we can also use it for numerical weather forecasting. Because, of course, if you want to use a model over the region, this is a prominent or key mechanism that the model should be able to represent.
Okay. I think another suggestion would be to also do a bit of work on the harmattan, because everybody concentrates on the monsoon system, but we have the harmattan is also considered relatively as a monsoon, some in quotes. So I think it's very important for our region. So don't only focus on the rain. I mean, if you can also do some work on the harmattan, I think it will be interesting.
Exactly. Yeah. So most of the time when we talk of the monsoon system, people think that it is only the summer one, but they forget about the winter monsoon.
No, they don't think that. They don't think that. Everybody is interested in the rain, so they just go with the rain.
Yes. Yeah, so it's very true that we look at the monsoon system as a whole system that prevails in the summer and then in the winter, which is on the edge in summer, and then another edge in winter, and then in spring and then autumn, we have a midway. That is exactly what this presentation is actually addressing. Yeah, so we have to, of course, bear in mind that we have what we call the summer monsoon and then the winter monsoon, which are equally important to be actually studied.
Yeah, okay.
All right, thank you, Prof.
Thank you.
Yeah, I think Richard also wants to have a question. So Richard, if you can unmute yourself, you can ask a question.
Yeah, thank you, Doc, for this interesting presentation. I would like to know what informed the choice of the 6 models. Is it the case that those are the best performing models and you are recommending them for future study over this region?
Okay, thank you very much. Actually, with the main work, I didn't use 4, but for the sake of this presentation, I restricted myself to only 4 of them, of the models that I used. In the main work, I used actually 8. I was restricted because I needed hourly geopotential high data sets. And it was computationally demanding to get that data set. So we went through the CMIP6 simulations or the data set that have been archived. And so far, we could only get only 8 models to actually where we have hourly geopotential data sets. And then not only on a particular level, we need it on almost all the levels. So it makes it very, very computational demanding to store that data set. And most of the CMIP6 models don't have that data set. That is why we're restricted to only 8 of them. And then out of the 8, I presented 4. Not that I actually selected the models that were doing well. In fact, I can say that the rest of the 4 actually did similar, but among all, what we can say is the model 1 in this presentation, which is actually in the case of the summer months, is not representing well these 3 features. So that is the reason. Yeah, so that will also call for the fact that we also need to get some of this infrastructure so that we can do some of this analysis. And in any case, we have all the codings on the GitHub of I showed you a website. So all the codings are there. So when you get the data set, you can, and it is automated. So you can just run it and then you can look at the output. Of course, this is the essence of the whole work, that we will develop a tool for this particular diagnostic, and then it will be embedded into the EVASA tool. And then anytime a model is run, you just connect it and then it will give you these outputs.
All right, Doc. Yeah, I think Prof. Lamte posted another question. He says, can you explain why you use the ERA 5 and then ERA interim as reference data sets in one case, and then ERA 5 and then MERA data in another case too? Why did you not use ERA 5, ERA interim, and then MERA 2 together?
Okay, all right. So in the case of the heat flow, I use ERA interim and then ERA 5 because they were the reference data set or the reanalysis data set that I could get the geopotential height in the format. I tried to use the MERA 2, but it was super difficult to actually get the geopotential height, and I mean it was difficult getting the geopotential height in the form that I needed. And then I didn't use CRU for the model evaluation because CRU, you see, is not giving me data set over the ocean. And then also as well, I didn't use the GPCC for the evaluation because GPCC is not giving me any data set over the ocean. And I wouldn't use ERA interim for model for precipitation or rainfall evaluation because ERA interim wouldn't do well. But of course, with temperature, it is quite okay. It is quite okay. And then, as you can see, the temperature in the ERA 5 and that of the MERA are similar, and therefore we could use it. But the precipitation, I couldn't use that one. And that is why I used the GPCP.
All right. Thank you so much. I think I'm not seeing any further hands raised. I think this is a really good presentation by Dr. Ano. We are so grateful for your availability to explain this particular topic, which I mean has really digested very well to many, I think. So without wasting much time, I think everyone will receive a link to this particular recording, and then also possibly if we have access to the presentation slides to also share to everyone so that you'll be able to link up. And also Dr. Ano is available anytime, whenever you want to ask any further questions, you can reach him so that he can really give you an answer to any question you have. Without wasting much time, I think it's now 11 a.m. and we are very grateful for everyone participating in this particular virtual seminar series. You know, we have more of the series coming, and I think we've been very consistent this particular year, you know, coming up with every month with presentations from different people. We are very happy. You also have time to listen to these various presentations. I hope everybody is clear by now. So I think it's now time for us to take some few pictures. So if you could turn on your camera, it would be very good for us. So that
I should stop sharing.
Yeah, you stop sharing. So that
yeah.
We can turn on our camera so that we can easily get everyone to take a group photo as usual. So everyone, please turn on your camera. It's always a good practice. Yeah, I can see some people not turning on the camera. Yeah. Yeah, waiting. Yeah, okay. So can I see a smile from everyone? Yeah. Okay, thank you so much for the time and then everything. I believe there are better things on our way to experience more and then learn. Yeah. So thank you so much. I don't know whether Dr. Ano, you still have something to say finally.
Thank you, everybody, for making time to listen to this presentation, and may God bless all of us.
Yeah, thank you. And then see you same time next month, the last Thursday of next month. See you for another great presentation again for another person. God bless you all. Thank you.